What's up, what's up, what's up? Welcome back. Today we are working on a re-implementation of zlib and zig. So zlib, compression library, lossless compression, uses the same underlying algorithm as like a lot of other stuff. Like zips use the same thing, PNGs use the same thing. I think it's like used pretty widely. And what I want to understand is like, how does compression work? Because it seems like a pretty core part of a lot of stuff, right? Like all of any like large assets should be gzipped. You're transmitting stuff over the wire. You should be like lossless. I shouldn't say should be gzipped. Should be losslessly compressed in some way, to save bandwidth, whatever, save storage. So, and the goal is if we understand how this stuff works, we can make better decisions, about using it when it makes sense, when it doesn't, blah, blah, blah. So today's topic is trying to optimize our like Huffman decoder. So what we understand so far is that zlib, he kind of has these like blocks of compressed data. Bloop, 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 bloop. And they might be either like no compression, which is basically just like a mem copy out when you're decoding or mem copy in when you're encoding. There's like, and then there's huffman. And there's like two types of Huffman blocks. Doesn't really matter for the purposes of today. And the idea behind this like Huffman encoding is, I guess I'll leave this arrow, is you have like some text that you want to compress, right? Imagine we have, let's say, B, 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 and then like maybe a C, an A, and a couple D's or something. You want to represent this stuff in a way where B's and D's take up less bits than C's and A's. And so what they do is you build up like this tree where you say like, okay, let's look at like the least frequent ones, A and C. Oh shit, sorry, thank you. Can't see screen, I forgot to transition. Thank you. Okay, so, sorry, I got lost there. Okay, so you take like the two least frequent characters, C and A, and you like stick them in a node, A, C, and then you can put these in like a tree with like more frequent stuff taking up less bits. The idea here is maybe you would want like D to be farther up the tree, and then like B to be over here, boom, boom. And you can like encode this thing as lefts on this tree take a 0, ones take a right. And then you have like this encoding where B is like one single bit 0, D is 2 bits, 1, 0, C is 3 bits, 1, 1, 0, and A is 3 bits as well, 1, 1, 1. And so this is kind of like where we're at right now. Our decoder will like build up this tree in memory. He'll store each of these like nodes here, and they'll store where he points to. So we'll have like a bunch of nodes that are branch nodes. And as we walk, we like start at the root, and we just like read bit by bit, and we say like, oh, we got a 1, go right. Oh, we got a 1, go right. Oh, we got a 1, go right. Oh, it's an A. And so today we want to see, can we speed that up? So there's like this like canonical version of the tree where essentially there are like rules about how this thing should be laid out. Right, so when you're building this, I could have chosen to do this very differently, right? We could have chosen to say B is here, and then D is here, and then A and C are down here, right? This would have like the same like compression level for the same text, except the codes are going to be different. So B is going to be 1, D is going to be 0, 0, this is a D, A is going to be 0, 1, 0, and C is going to be 0, 1, 1. And so like you can say, okay, we'll make rules about like the layout of this tree to make it so that everybody always comes to the same answer if we just tell you how many bits each character takes up. So they represent it as lower bits always take the left branch. So here we should say B comes before D comes before A and C. And then the rule for like same bits is that lower like values should come first. So A should come before C. And what ends up happening here is for all values of the same bit width, you end up with a sequential chunk of codes, right? So this is going to be, 1 1 0, and then C is going to be 1 1 1. And if you had like a tree that was like a little more balanced, let's see if we can draw a more balanced tree somewhere. So I think that you would need like boom, 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 boom. Say they all have the same frequencies. You would do A comes first, B comes second, C, then D. And then you get the values of like 0, 0, 0, 1, 1, 0, and 1, 1. And it's just like sequential values. Chill. And then if this was to like end up, if you ended up with like one more character that you wanted to encode with like more bits, you would like put this in this node here, 0 goes here, 1. This is a bad example, but this would have to like kind of end up as 1 1 fuck 1. We won't draw this way because I can't hand make the tree in my head. I accidentally dragged this bar out and this fucking pisses me off because I don't know how to get it back in without just like resetting a file, and I can't remember where it is, so that's gonna piss me off like the whole stream. That's okay. So anyways, the point is this tree should be built up of like sequential values, and we can exploit that to decode using an array. And so my thought is, if we start with like arrays that are sorted by number of bits used, so we could say like, this is our 7-bit array, and this is our 8-bit array, and this is our 9-bit array. I think that we should be able to store a pretty small amount of data. We should have like arrays that don't have like holes in them at all. And we should be able to immediately skip to decoding 7 bits at a time. And instead of like walking this complicated tree, we should just be able to like O1 into wherever the text is. It's kind of the thought, what I want to try today, and we'll kind of see how it ends up. We'll see where it goes. And plan of action is like, just do it. Like, there's not really much of a, I can't see, I haven't seen a way to like break this down, but maybe we'll discover it as we go. Okay. So this is our Huffman table. Before we had this like structure of nodes where we shoved nodes into an array where a node could be either a branch or a leaf. And then we just stored the index of the root, and then we would walk the tree by basically like updating our indexes, whatever. We would like look at like, if the root was at index 0 in this array, we would like, let's see, let's go delete, and then we go, right, if we have like node, 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 right, if our root was like here, we would say, okay, is there like a right or a left that we have to take? And then it would say like, oh, right is 2 or index 2. And so we'd go like, okay, now we're here. And then we'd say like, do we go right or left? Right is 3 over here, whatever. So that's how this is stored. And so I guess we just replace this with something else, right? We just kind of like destroy this and replace this with like, how do we want to call this? So I'm thinking that for each bit width, the storage is kind of like one for, so we know that the lowest bit width is going to end up with like value 0. And this is going to like increment sequentially until we get to the next bit width. And when we get to the next bit width, we are going to start at 1. The first bit's going to be a 1 because we have to take that right branch. And I'm not quite sure. I don't know if this is like 1 0 0 0 0 0 or if it's something bigger. And we can maybe like take a look actually before we do anything. Maybe we look at we like look a little closer at the Huffman codes that are generated for a table that we already know about. So maybe we do something like we have this fixed Huffman table that is part of like the zlib spec that they kind of like everybody agrees on to share. And maybe we just take a little peeksies at this guy. Why is my jump to definitions not working? I'm not in a Nick my development environment. I believe the maximum code width that you can have is 15 bits, which is one of the 15 element array. Oh, so one should be left by 15 element array. I think that's is that true? I think that I don't need that many elements. That's my guess. I want to double check this, but I'm pretty sure that I only have to store as many elements as there are codes. I think. And that's what I just want. That's what I'm trying to prove here. So let me take a look again. So zlib fixed huffman table. Where is this guy generated? Here, get fixed huffman table. Let's just like print this guy out. So we'll make this guy public, go over to main, and just say, hey, could we get fixed huffman table with some allocator? And this is a failable thing, so we have to try defer table d init. If true, returns that we don't run the rest of our shit. I don't really care about it right now. And then let's just kind of table. We have to like generate. I have the code for this already. Actually, let's just do this. So there's like this confusing behavior where our blocks are kind of how to say this. So the code is going to be like 1 0 0 0 is going to be right, left, left, left. But the order that we're supposed to read these things from the file are from least significant bit to most significant bit. So this will actually end up as like 0 0 0 1, which kind of like adds some complications because you need to know how many bits to read this way. Anyways, I have like some code for this that we wrote the other day, and then I copy pasted it into unit test offline. So let's just copy paste this out. So this is going to be, this code is probably what we want. And then instead of doing a testing assertion, let's just print the code. Print stud debug print this thing as binary, I guess. I guess we can print it as decimal. And I guess we want to print the code, the item as well. So this is, I guess I want the index. I want the index. So let's just grab that real quick. This is supposed to say start, maybe? Begin, no, begin. And end, and then we can just print that I gets this code. He doesn't like that for some reason? I don't know why. I thought this was a valid way to do a for loop, but let's see. He says unused capture I, but I'm definitely, oh, I'm an idiot. I just wrote I here instead of, oopsies. Oopsies. There we go. Zig, build, run. Let's see if this prints something sane. Yep, okay. Cool. So we get 23 contiguous things at this range, and then this gets, oh, I actually do want this in binary. Hold on. So let's print it in binary, and then can we do something like, I want it to be 8 bits long, aligned to some direction. 0, I had it backwards, so I want this arrow to be this way. Okay, cool. So we have 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, blah, blah, blah. We're incrementing. And then here, when we jump up to the next bit width, we get the 1, 1, 1, 1, 0, 0, 0, 0. So how is this working? Then these guys are sequentially incrementing up like this. And I think that if I remember the code that we looked at for canonical Huffman coding on Wikipedia, I think that this is he does code +1 shifted left by 1. Right. So it doesn't start at 0. It starts at some value, but then from the starting value for this bit width, it is incrementing sequentially. Each value at that bit width is 1 more than the last one. So I think that we can do something like, in our storage, we can do something like, hold on. You have something that's like bit width, something. Vals for bit width. Sure. We'll figure out the naming a little bit later once we've like fleshed out a little bit. And in here, we're going to have items. No. What do I want to call this? Vals. And this is going to be like some dynamic array of t. And we're also going to have the starting offset. And so the idea is we can do like a lookup in here. It takes in self by pointer, but this is not going to be called self. This is going to be called like vals for bit width. And we're going to return a t. But the t might not be there, so it will still be an optional t. And so what we can do is we can say, given some code, can we get out the thing? We can just look up self vals items len. If the length is greater than or equal to the code, we say, hey, this is not the right bit width. And I'm thinking that if we do that for this bit width, we'll like move up to the next bit width. This should be code minus offset actually. Var index const index is equal to code minus offset. Yep. Okay. I think that makes sense. Like the idea being that we're gonna have like bit at like 7 bits in this example, we're gonna go from codes 0 up to I think it was like 24 or something. And then at bit width 8, we're going to go from values like 48 to 60 or something. Doesn't really matter. Like, there's just going to be a gap in here in numbers. And so the indexing into 8 has to be like, we have to subtract this 48 to get into the array, I think. Otherwise, we can just return self vals items at index. Cool. Sure. And then our vals by bit width is going to be a structure which holds an array list of vals for bit width. Yeah, vals for bit width is going to be stood array list vals for bit width or something. And I guess we need to store as well the bit width for this thing. Yeah, and then this doesn't have to be a structure. Unless we want to be able to like attach some functions to it. Which we might. So let's say that in here we want to do something like lookup vals by bit width code usize, and this is going to return, maybe this fails in some way, and we're going to start with like the smallest array. So we're going to assume that these are sorted by bit width, I guess. we can say self vals for bit width for each element in here. And I think that I have to put an ampersand on here to iterate by reference. And then here, this should be vals. We'll just call this items. I don't know. Doesn't fucking matter. Doesn't matter. So we'll call this vals for bit width, or maybe we'll just call it item here. I don't know what the type of this thing is, but I guess we'll find out. We're gonna say that we're gonna like look at item lookup for our given code. And if this gives us a value, we return the value. I don't really like this that much because what's going to end up happening is when we're actually doing our reading, we are going to we're going to start by read like 7 bits, right? And then we're going to say if 7-bit lookup had value, great. Otherwise, we're going to read one more bit. Read one more bit, try again. And so, like, this here, we should kind of know which lookup we should be looking in, if that makes sense. So maybe this, like, lookup function here doesn't really make sense. Maybe, well, maybe here we'll just say, bit width or something. And then here we'll store, like, min, bit, width. And then now it should be easy to say self min bit width minus bit width is which one of these guys we're gonna look into. So we'll call it something like this. And then we can just do self items table idx lookup code. I think that makes sense. Okay. So now we should be able to store a vals by bit width here. And now we have to like initialize this thing. So I think the initialization code should be significantly easier now. I'm going to, for now, just make this empty in like the one of these paths. Vals by bit width. I'm just going to make this a empty array. So can I just say, I guess I'll just say undefined for now here. And I think when we init from bit lengths, it should be pretty easy to populate this guy. So how do we want to make him? So I think that we have a sorted list of items and their bit lengths. So I think we should just be able to do something like for element, what is it? Here. Okay, so for each element with its length, this is equal to elem lengths items I, and I think we put a little pointer on here so that he is not copying out. Not that I think it matters, but it's fine. So this guy has elem with bit length. Elem with bit length should be elem and bit length. Okay. So I guess we'll say min bit width is equal to lm lengths items 0 bit length. Okay. Okay. And then we'll say that our, what do we call this thing? Vals, or vals by bit width, is going to be an array list of array lists for bit width init allocator. Okay. Yep, this is all fine so far. And then each of these guys, we're going to look at his bit width, bit length, bit width. I don't know what I'm calling them here. Bit length, we call it here. And we can say it while vals by bit width length is not minus the min bit width. So here we're trying to like push in new arrays so that we have a valid one to work with. Are you listening to music? No, should I be? So while this is, I guess this is while min plus min bit width. Here we go. Yeah, while this is less than lm length bit length. Is that right? I guess we want to calculate offset. So const lm length offset bit vals by bit width idx, I guess we'll call it. This is going to be my bit width minus the minimum bit width. There you go. And then I guess we can probably unconditionally resize this thing to be big enough for vals by bit width index, because this is going to be always incrementing. This will just reset the length, and ensure total capacity should be fine. Okay, yeah, so I think that'll be reasonable. And then we should be able to do something like vals by bit width at vals by bit width idx. Yep. So this is vals 4-bit width is equal to this. And then we can push in our specific element into this specific array. Trying to guess what the earphones are doing. Oh, I mean, I just like having them in. Just in case, like, my desktop happens to be playing music, like doing something, I want to be able to hear it. And it's just like, while I'm at my desk, they're always in. It's just kind of by habit. Okay. So here we're trying to push in this exact element. So we're trying to get to the point where we have, like, say A, B, C, and D are taking in, or maybe we'll skip a letter. A, B, and D are, like, very frequent. Then C is less frequent. So we're kind of trying to say, like, we have, like, these two arrays. This guy is 7 bits. This guy is 8 bits. And we have, like, some offset for each of these. So vals 4 bit width is one of these inner arrays. We're going to just say append the element. Okay. And then I think I'm missing something here. I have to assign a bit width in here somewhere. That's okay. We'll get there. So this guy has vals by bit width. He needs the items to be vals by bit width, and then the min bit width to be min bit width. Okay. Zig build. I'm sure a bunch of stuff isn't working right now. Resize error is ignored, so this has to be try. No field append in this thing. Right, so this is like a... he has vowels. Yeah, he needs to append to vowels. And this offset is not well defined. I'm gonna have to figure that out as well. I guess it's something like this, where we were walking code lengths before. No, not really that. Sorry, just thinking. So we need to assign, if we need to insert new thing, lm length dot. So if our index is less than vals by bit width items len, there we go, or is greater than or equal to, we resize this thing, and we have to set a couple things. We need to set the offset and the bit width. So the bit width is easy. Bit width is just lm length dot bit length, okay? But the offset is going to be confusing. But that's okay, we'll figure it out later. Because there's something to do with this, like, left shift and add 1. So I guess we can just code equals 0, and we'll just do this same shift here. Sure. Yeah. We'll just do this. We'll just do the same thing here. So we say next bit length is this. Every iteration, we increment the code. And the offset is just the code number, I think. We'll see. I'm just trying to get like something down and we can iterate after. Okay, does this build? Undeclared identifier lm length. So let's just go down here. And this thing does not support indexing, so these guys have to write dot items here. And no field name val in struct item with bit length. So what is it? It's lm length dot lm, not dot val. Got it. Okay. So we compile, and maybe for now, we just print this guy out and see if we get what we expect to see. So here we can say, table vals by bit width, and let's just print this thing. I think it's like this. Zig build, run. There we go. Okay. Index out of bounds. So where is this coming from? This is coming from Huffman to Zig 201. And that's here. This has to be +1. I fucked up. Okay. So now integer overflow at append here. Why? What is What could possibly be overflowing? Mem, align, resize. I must be pushing like way too fucking much. Somehow. So this is at line 206. So here, he doesn't like this at all. Oh, because I probably have to initialize. Right, I have to initialize this whole thing. So this is going to be vals is equal to stood array list t init allocator, I think that's right. Okay, that's better. We got a leak, but I think we at least got something that's sane. Okay, so what are we expecting? We're expecting to see 256 to 279 in the first array, and then 0 to probably 0 to 143 in the next array with an offset that makes sense. So let's go back to main. And instead of printing these things as binary, let's print them as decimal. So we should see offset 48 in the second array. That's what I want to see here. So he's printing. This thing's not printing what I want to see. He's like hiding some internal details here. So let's say, can I say print items here? And will that be a little bit better? Bit width 7, offset 0, right? And then the next thing is bit width 8, offset 48. That's a really good sign. And then we have bit width 9, offset 400. Okay. And is offset 400? Does that make sense as well? It also makes sense. We go from 199 to 400. So that's a good. The offsets are being calculated correctly. And now we just want to check like the internals of these things. So let's look at the 8-bit table. Huffman table array list is not. Oh, this would be like items again or something. Vals, items. Look at that fucking line of code. Table, vals by bit with items, items 1, vals, items. Sick. Okay, so this goes 0, 1, 2, 3, 4, blah, blah, blah. He goes sequential until he hits a certain point, which is at 143, then he jumps to 280. So I think that that's what we expect to see here as well. We see 0 to 280. 143 jumps to 280. Great. So I think that the data is now like in the Huffman table in a way that makes sense. And now we should be able to implement our Huffman reader like in terms of that new data format. So let's say here we are at 3855. And we want to use arrays during Huffman decoding. Okay. So before, what this guy was doing was he was basically just setting his node index to the root of this tree. And he was just kind of going bit by bit, reading one bit at a time and branching left to right. If you saw a leaf, you'd go, okay, I'm done. And so now we kind of want this to change to what? He's going to get the minimum number of bits. Okay, so you can say self table vals by bit width min bit width. And he's going to read this many bits from the file stream. Yep. and it needs to read them into some value. So I guess we'll just do U64 for now, because I'm not really sure what we are going to end up needing. And then we're going to ask it for how many bits it read, I guess, because that's what we do up here. And then we can assert that the number of bits that we read is how many we actually wanted. But I don't think that should make a real big difference. And then we're going to say var offset is equal to 0. Okay. And the idea here is we are going to look at the tables. We're going to look up the thing we read, which is, I guess we need to get the thing. Var idx. I guess it's a U size is what makes sense here. And we're going to look up, I guess we'll call this code, the Huffman code. We're going to look up the code in the table. Yes. And we will also have to specify how many bits that we expect to read. So we'll say self table vals by bit width, min bit width plus offset. Instead, we'll just call this bit width here, and we'll say that this is initialized to this guy. Okay, yeah, that makes sense. We need to swap the bit order of code. This is important because the codes are sequential with... So if you have like a tree that is encoding right, left, 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 right, right, or something, right? They are only sequential in value if they're stored in this direction, reading left to right, right, left, 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 right, right. But in the actual file, it's encoded backwards. It's, hold on. It's encoded as go right to left, so right, left, 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 right, right. So you have to like do this like bit reverse thing. So I'm just gonna copy this line here, but this should be factored out. And this should be code here, and code, and number of bits should be num bits like this. Okay. Okay. So we look up the code, and then we give it the bit width. And while this is null, which I think you just say equals equals null, how do we want to do this? While this is null, not code, reversed, I guess we'll call this reversed. We read it reversed, and then we reverse it to get the code. I think that makes more sense. We should be able to basically left shift this thing by 1. Left shift by 1. And then add in one more bit read. No, we don't do any shifting. Sorry, we or in one more bit read. So we'll say read bits usize 1. And then here we will assert that the number of bits that we got sure is 1. But then we need to shift this left by number of bits plus 1. And then num bits plus equals 1. I think that makes sense. And then we should be able to say return this guy. I think. Not really sure. Not really sure, but it's possible that that's right. So the idea here is that like we start on the lowest version of the array, the 7-bit code version, and if we don't see it in there, we read one more bit, and since this guy's supposed to be like 10000, and then we're like we read one more thing, so we want to put it like at some like one more bit read, like 11000, and I think that should do what we want. I think. But there's lots of reasons that this could be wrong, but I guess we can just run our tests and we'll kind of see how fucked it is. Okay, so we are forgetting to write try in some places. So try here and try here. Okay. Here our lookup needs to allow us to take in this thing by const, because he's not modifying anything, he's just looking stuff up. Okay, we need to int cast these guys because he can't prove to himself that this bit shift will be allowed. So here we say, hey, truncate or yell at me if this is a bit invalid shift. Okay. Now we're hitting unreachable code. We're asserting that we're trying to read some amount of bits, blah, blah. You've done the bit reverse before you read in the next bit. I think that would mess some things up. I don't think so, because I think that I'm like copying. I've got like file stream of like some amount of things in, right? I'm copying this out into my own local variable, reversing the bits, right? So my local version of this doesn't affect the file stream at all. And then I read in one more bit, and I just make sure to put it on like most significant bit instead of least significant bit. So I think that it's like totally fine. I think. I mean, clearly it's broken in some way. So, because my tests are not passing, specifically test Huffman back and forth crashing, which makes sense because we wrote a bug in here. I wonder if we could debug this. Zig build. I think that this should create a test binary that we can run somewhere. So I think it's here. Yes, I think that we can just run this. Perfect. And then if I run GDB on this guy, can I specify like a test filter in here? I was looking at the Zig code base the other day, and I think I understand how like this test runner path works. It's pretty crazy, actually. I think what happens when you run these tests is you have some file runner.zig. This guy, he is like compiled in to the context where all of the unit tests run. So I think that you have like this thing, you write like test in Zig right there, like this, and you put some shit in your squiggly braces. And this, I think, turns into a function pointer. So this guy goes to like, he basically looks like function ... Your test runner can access all of the tests that were compiled in this translation unit, which is like the whole thing, like essentially, by this like built-ins variable, built-ins.tests or something. And like this test runner essentially just like iterates these tests and runs the function pointers, which is how I was looking into this, because I was like, how the fuck does the test fail when I forget to dealloc? And it's because in like the default runner that they give you, he creates an allocator in the global namespace and then just checks every time, like, or sorry, not global namespace, like a global variable. He just like creates a global variable that is an allocator, and it happens to be instantiated by the time you get here because he does some like setup in main. Yeah, so that's kind of how anyways, we're sidetracked. I was about to go look at the default test runner, and so I was like, I'll give you background on how the fuck I figured this out the other day. I think this is here, test runner. And so does he do anything with his arguments? He has this like -- listen argument. But it doesn't look like there's any like test filter. Because here I just like iterate the test function list. And so probably if I were to filter in some way, two-step is saying that I should be able to run zig build test with -d test filters foo. So probably if I run with -d test filter, my guess is that the zig compiler would choose not to compile those tests into the binary that's generating. That would be my guess. And my guess is also that if I were to run GDB on zig build test, based off what I know now, my guess would be that zig build also might run in the same... No, it can't run in the same namespace. It would have to fork to run the test binary. Pretty sure. Because the test runner has a main. So zig build also has a main. So it probably forks to run the test after it compiles it. And so GDB would have to know to follow forks. But we can try it. I'm curious now. You need to set test.exe.filter equals b option in your build.zig for that to work. Whoa. Okay. So you're saying that if I go into zig, my zig builds file, in here, this add tests, I can say like test options has a filter function variable on it. And this guy is probably just specifying, he's like attaching that to some compile command. Let's create options filter. Right. So find references. So in my compile creation, if I have filter, what do I do with that? And by I mean the zig compiler. My find references isn't gonna fucking work here probably. That's annoying. Okay. Let's see. What we could do instead, zig test help. So here I can put some test filter on. And I think that I can ask it to emit a binary for me. Emit. F emit bin equals this. Yeah. So I can say zig test source main. So if I run this, oh, but it doesn't have all my compile options. No. Okay. This is so fun. Zig build help. He's going to tell me. Yeah. I think I'm starting to see what you're talking about now. So can I just like add my zlib path manually? Is that going to be faster? It might be faster. It might be. So that's going to be this guy, I think. Can I just say like zig build test or zig test source main this unrecognized main.zig? Okay. libc header is not available. Fuck. Okay, we're going back into the build script. Dash lc. I don't know if like, is it already? Oh, okay. It already knows. So now I need to lz as well, probably. There we go. Okay. Sick. And so then we can say test filter equals Huffman. Test filter. Fuck. Zig test help. Filter. Test options. Dash test filter. So why didn't you like that? Oh, because I said equals. I have to do test filter Huffman. Ah, yeah. So the fact that it does rebuild there is an indication that my guess was right. And so I can like test Huffman back and forth. Like, is this going to only test the one thing? Test 2 out of 2 instead of 2 out of 5. So there's something there. And then if I say f emit bin equals test, then this should create a binary test that I can run. Perfect. That was a fun little adventure. Okay. And then here we can see that we are in this like test runner running test Huffman back and forth. Okay, cool. Cool. So all of this was because I wanted to run GDB and debug something that wasn't working. I don't remember what. We got like so fucking sidetracked. But we're there. We're there now. So it was that I wanted to debug this Huffman reader. I wanted to debug what the hell is going on here. So break on huffman.zig 478. Run. And if our test filters worked correctly, we should be in only test Huffman back and forth. Look at that. Very nice. Okay. So where the fuck am I? We're at line 478. So we're here. Next. Okay, so let's start by looking at the code we got. No binary px code 0x15. And the bit width is fucked. Okay. Table vals by bit width. Okay, let's just take a little. Oh, so this is just unset. Oh, fuck. So our unit test is just on the wrong path. Right, because I just didn't fucking populate this. So of course this test is gonna fail. God fucking damn it. Because, test Huffman back and forth is using our initializer that's based off of character frequencies. So can we, okay, here's what we'll do. We'll comment this out for now. And run. Init from bit lengths. And how do we want to do this? We need to generate bit lengths for each of these guys. So let's do something like var bit lengths is equal to 256 characters of U64. There's 256 options, and then we'll just assign them. So bit, I guess this is going to be how do you do this? You do like a single element U64 array of 0 with a double star of 256 or something. So this is like copy this 256 times to make a 256 byte array or something. I can't fucking remember. And then we just have to go through a SDF, and then we can say bit lengths A is equal to 2. So all of these should get 2-bit, I think. I think, and then we can just pass in bit lengths or something like that. Okay. Cool. So now we're probably getting something a little bit more sane. Can we look at frame 6? Okay, so we have code 4, which should not be valid. But maybe this isn't a valid table. Okay, let's go back. We're going to init from bit lengths. We're going to get the table from, does Zig have, like, issues with recursive imports? I hope not. We'll see, though. Because I just want to use a different table. I want the get fixed huffman table, this guy. Okay, let's try that. And then, does the rest just work? Okay, no field, remember, blah, 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 because I forgot to write try here, probably. Append, output, append. Here, this is just going to be an int cast for now. Because from a U16 to a U8, we know that it's going to be all U8s. Probably, I think it's going to be all U8s. There we go. Okay. Index out of bound. Index 82, len 24. Okay, so this is 46. He's going from index code to offset. If the length of this guy is greater than or equal to the index, then we return null. And then he's going, but then I index and it fails. So why the fuck would this index ever fail? Unless there's a bug. Okay, let's GDB. Run it. Backtrace. Frame 8. P IDX. P self vals items. Length is 24. So, hello? If self vals items len is greater than or equal to index. Oh, I'm an idiot. I just had the fucking condition backwards. As always. It's less than or equal to index. Yeah, there we go. Let's try that again. He's now crashing. We can just GDB it again. Okay. Frame 7. So we read 2 bits. Even though we explicitly asked for... How many did we ask for? We asked for 2. Hold on, what's going on here? Numbits 0. Oh, sorry, we got 2. We asked for... let's replace these with bit width here and here, just so that they're easier to read. And then let's compile it again. He's going to fail again. And we're going to run it. Backtrace. Look at frame 7. And print out numbits. We got 2 at line 489. So that's here. So I explicitly asked for 1 bit. Oh, I'm an idiot. I just fucking incremented the wrong variable. Incremented the wrong variable. This should be bit width, not num bits. Let's try again. We'll try it again. Now we are just getting an integer overflow on this subtraction here. So let's take a look at that. Frame 6. Here we go. So we have min. We have the bit width that we asked for, which is 8. And we have the minimum bit with the 7. So we just have this like subtraction inverted. We were trying to see how figure out our offset, and we just fucking got it backwards. Here we should be subtracting the other way. And thank God for nice little errors like that. I'm happy for like the integer overflow checking. That's sick. Another integer overflow. So let's see what's going on there. So this is at frame 6. P code, P self offset. Okay, so here's a bug somewhere. So we are trying to read code 40 with bit width 8. So we're looking at the second table, code 40, which shouldn't exist in the data. Although if this shouldn't crash the program, this should result in like an error. So let's fix that a little bit. So we can say if code is greater than self or less than self offset, we're going to return an error. Invalid code. Which means that all of these guys have to propagate errors. And this guy has to write try here. So that doesn't actually fix the bug, but it does at least prevent us from crashing in this like particular error case. Zig test. Here at 494. I guess we just write try here again. I guess we can actually say var ret is equal to this, while ret is equal to null. And then at the end of each loop, we do this assignment again so that we can return ret here. Okay. Not that that fucking matters, but... Oh, wait. Oh, yeah, he says fail, invalid code. Oh, interesting. So now the test actually passed, or it like runs to the end, and so now we get like errors about memory leaks and stuff, but it's crashing differently now. And that's kind of weird that we don't actually panic anymore, which is kind of surprising. I guess not that surprising, because returning an error is like a valid case. Okay, so now we should take a little bit of a closer look at what's going on in this loop. So let's break at line 489. And okay, so we got data. Oh, I've never looked at this like optional encoding before. That's kind of interesting. So their optionals are 2-byte values, I guess. Like they basically come out as a struct where you have the actual data and if the thing is null or not. Cool. So our initial code is 82. Then we say, that was too big. Our 7-bit table only has, I think, 42 values. Let's look. Self table vals by bit width. So our first table, items 0, dot pointer, 24 items, sorry. The first thing only has 24 items, and we had code 82. Can we print in binary 82 just to get a little bit of a feel for what that is? So can we say like, how do you do this? You say 82 as a Boolean. So this is 1, 2, 3, 4, 5, 6, 7 bits, and it's starting with a 1. Okay, so we expect this to fail. We expect this to say, I don't fit in this array anymore. Let's check the fucking 8-bit array. So can we kind of step through and see what happens here? So this is the dangerous part, that there could easily be a bug in here. Easily be a bug in here. So let's print this and then print code again. And code is still 82, which is surprising to me. That means that we must have read a 0 or fucked up our shift. Both of those are very real options. So what we can do here is we can split this out. Next bit is equal to this. And then we can use next bit here. And is this the right spot? Yeah. Zig test. And now what I'm hoping is that we can look at the next bit and get a clue about something. I don't really know what yet. Okay. So here, next bit was in fact 0. And we did read 1 bit. Okay. So what the fuck is going on? Let's think. Could you use CLZ to get the bit width? I'm not sure about that. Not positive because I'm not sure that it's guaranteed to have 1s on the left side. Not positive. I'd have to think about it a little bit. Okay, let's double check the test to make sure that this test is like using sane code. So you could have a code like 00, so I don't think so. Right. Yeah. You're right. Because like the 7-bit, like the lowest bit count starts at 0. And so you need to keep track of it externally. Right. Okay, so we have some table, and we generate a codebook from it. Okay. And then we write in. Okay, so we generate a Huffman writer where we write our input. This is a test string. And so I guess what we should look at is we expect to see the value for t in here. So maybe we can like look at the codebook to find the value of t and see if it lines up with what we expect it to be. When you write in the extra bits, you shift by num bits. Is that correct? Certainly not, right? Yeah, certainly this is wrong. But I think that the fact that we're still reading in a 0 feels wrong to me. But we can check. So let's run this again. Breaking here, run. And let's look at I wonder if we can figure out where the T is in this code book. Actually, I think what I want to do is I want to break somewhere else. I think I want to break in the test when we generate the codebook, and then we can just look at it. Codebook. Items. He has 288 values in him. Okay. So we look at pointer at 288 to print 288 and star him. Okay, we don't want to do that. That's too fucked. And then can we do like pointer plus the letter T or something to get us the offset of T in the codebook? So he is value 37 with numbits 8, but we have to remember that we are back in this situation where we have to read right to left instead of left to right. So can we look at this thing dot data val? Whoa. Why can't I? Oh, because I'm an idiot. Star goes here. Okay. 0x25. Let's go Python land and format this guy as a binary value. And then so we should see 101001 41. So this is kind of interesting here. This feels a little fucky-wucky to me. Where the value of t... What is the ASCII value of t? ASCII value of t is supposed to be hex 47. 71. Okay, so if we go back to our printing of the code book, we should be seeing that the value of I got lost. Man, ASCII. T is hex 4t7, which is 71. So the value of 71 in here should be code 119. So this is the value that we should be writing when we see a T. I guess we don't really know that this is the value that we're trying to read right now. We should look at was this the bug we were seeing before? Index out of bounds, length 3. This doesn't feel like what we were seeing before. Maybe. Oh, but we were breakpointing before, right? We were breakpointing at huffman.zig, like 491 or something. Yeah, okay. So here... I feel like I'm missing something obvious here. So the value of t should take 8 bits. I'm pretty sure that that's correct. Deflate RFC. Okay, here we go. Yeah, because t was value 71, which is in the 8-bit range. Okay. Okay. So we try the 7-bit ones, doesn't work. Fine. We start at 8-bit, and I guess we are seeing that there are values that have leading zeros here, so that's okay. I thought that it should always start with a 1, but I guess that's just not true. So that makes sense, I guess. Problem is we get code 82. Code 82. Which is... Do I want to print that in binary? Maybe I do. So that's 1010010. 1010010. It looks like it should be in this range. How do I want to... I feel like I'm thinking in the wrong space. Thinking in the wrong space. Is it possible that this is actually fine? Like, does this find something? P red. Oh, okay, this did find something. Okay, so that's interesting. But the data is 34. Which is not what we thought it should be. Okay, how do we debug this? P code 82. This is the first value being read. And we know that the value should be a T. Okay. So we can check what we wrote, decode it by hand. And use that information some way. So we wrote this stuff into this buffer. So we can look at pbuff.items 0. .items.pointer. We can dereference this thing. This is 37. Okay. We can look at our codebook. And we can look at the items pointer plus the value, the ASCII value of t. This is 37 with 8 bits. Okay, so the first value, 37. 37. Everything there makes sense so far. The thing we wrote is the t in test. Okay, so why the fuck aren't we getting it back? Okay. So the code we read, 82, which we have to actually reverse the bits in 37. So, let's go back to Python land. 37 as binary. And then we go 101,001, and we need to make sure it's 8 bits. So this is 1, 2, 3, 4, 5, 6. So we need to add 2 zeros here. This is value 164. Okay, can we see if we see any patterns in the code that we got? We got the code 82. So what's going on there? Is there anything in here that looks about right? 101, 101, 001, 001. With an O at the end. 101, 001. We're just missing a 0. We're missing a 0. We're missing a 0. Okay. Whoa, okay. So now that's a fucking thread to pull on, baby. We're missing a 0. So why? Because we have to shift left here. We have to shift left after we do this. Because the next bit we read in should be at the end, not the beginning. Oh, okay. So I was going 1000001 or something, right? Let's just say that this is what we had read in. And I was like, I need to read one more bit. And I was sticking it here. But it had to go over here. And I think somebody called that out, like, right when I fucking wrote this, and I was like, nah. Okay, so code is shifted left by 1, and then code is equal to code shifted left by 1 plus next bit. I guess we can even do or next bit. I don't know which one of these ends up being faster. My gut says or, because I'm trying to help out the compiler to know that this can only be 0 or 1, but in reality, it doesn't fucking matter. Doesn't fucking matter. All right. So does this actually fucking pass now? Integer cast truncated bits. This is like 486. Interesting. So I don't know if we got farther or not. This feels different. So can we look at who is complaining here? do we not? We might not get the actual values in here, but we can look at num bits 0. Okay, wait, why is num bits 0? Oh, fuck off. I keep using num bits, which is the number of bits that we read, but I wanted to use bit width everywhere. So num bits should like literally like not be fucking used. Okay. God damn it. God damn it. Okay. Now we've reached unreachable code through reader.next, where because num bits is not equal to bit width at line 487. So we didn't read as much as we needed. So we read 0 bits here, which is surprising. So what happens here? So we read 0 bits. So we said, hey, if we have read enough bytes here, return. But then he's saying, hey, you think that there should be more data here, but when I fucking read, I get nothing back, baby. And I guess it would be interesting to see how far we've made it here. So we can actually say test GDB run backtrace frame 7, and we can look at, well, how far did we make it? Which is, what variable is that again? I fucking lost it. We are at 44. I want to see self bytes read 0. Okay. That's surprising. Bytes read 0. Oh, maybe I just never fucking increment that. Yeah, that would do it. Because before we were keeping track of it as we retrieve bits, but now we are not. So we have to... we have to keep track of this now. So maybe we say maxlen in bits now. And we can call this bits read. And then every time we look at num bits, we can say self bits read plus equals num bits. Boom, boom. Okay. This is maxlen bits now. And then when we construct our Huffman reader, we need to say maxlen bits is equal to maxlen times 8. Okay. Okay. Self bytes read. This would be bits read. Oops. Bytes read. This would be bits read, not bytes read. Bing, bang, boom. Okay. And now how fucked are we? Hey, all we have is memory leaks, which might mean that it works. That's very possible. Hell yeah, baby. Okay. Let's look at our... Let's just try to clean up these leaks. Table deinit, codebook deinit, output deinit. What's it fucking complaining about? So this is from... vals for bit width. We have to clean up our memory. We just didn't do that. So here in our Huffman table, we have all this new shit. New shit just dropped. And when we de-init, we actually need to clean it up. And do we just want to get crazy with it? There's like a bunch of nested allocations here. But what if we use these fancy schmancy arena allocators and we use this everywhere. So we take in some allocator on initialization, and we say we'll call this child alloc, and then we'll say var alloc is equal to self, nope, stud mem arena heap arena allocator init with child alloc. Okay. Then here we store our allocator. And then everywhere where we take in our allocator, I'll fix it later. Then we can just say self alloc d init. To 19, we have to do the same shit. So in the other init path, take an allocator. We call this child alloc. Var alloc is equal to stud heap arena allocator child alloc. Oh, see, this is dot init child alloc. Okay. Expected, type this, found that. So this is at 131. So we have to call this arena and then say var alloc is equal to arena dot allocator. And then here at the end, we say alloc is equal to arena or something. Nice. Nice, baby. And then we don't have to dealloc nodes. There's everything, all the memory just goes away. That's kind of a nice little tricksy. That's kind of cool. So I'm just basically saying, like, I don't give a fuck. I don't give a fuck. I'm not going to track all this shit. You deal with it, arena. Okay. Okay. So I think it's working. Zig build test? Question mark? Integer overflow at this guy. Max len bits max len times 8. Oh. Oh, because I'm cheating somewhere and I set the maximum length to usize max because I didn't want to deal with it. So we can just say if max len is equal to usize stud math max int usize. We return max len, else we return this thing. Okay. Is Zig going places? My gut says... Oh, I guess I have no fucking idea. I wouldn't bet on it, personally. I think that... I think that it's good. My impression so far is that it's what I wish C++ was. And I can say for sure that at a job, I would never try to push Rust. No matter how much I like it, I would just never fucking do it. In the same way that I would never try to push somebody to use Vim, or to use Tmux, or to use Nix, any of the tools that I use, it's like, I would never, like, inflict that upon someone who didn't ask for it. And so I kind of, like, feel like Rust falls in that boat where it's like, holy shit, I love the guardrails that it provides me, but I can see a world where I'm like, hey guys, we should use Rust, and then everybody just fucking hates you because they're like, what the fuck? I just want to write code and I can't write the code I want to write because like this like lifetime management, this like mutability management, it's all fucking getting in my way. I just want to write the code. Where I feel like Zig, it feels like it's kind of picking this like it's hitting this like pragmatic middle ground where like it's doing a bunch of safety checks that I like. It's like organized in a way that I like. And so like I would recommend Zig at work if it was more stable, right? If we were like farther into the release cycle, right? We are like, hey, hit 1.0, we know that things aren't going to go away. And so there's definitely something there where like I feel like there isn't another language that I've tried so far. I mean, I haven't tried a lot, but like I haven't used something else that I feel like could take over the C++ realm without pissing everyone off. And Zig, I feel like, is filling that very well. It like unlocks a bunch of the like meta programming stuff that you would have to do in C++ with like Sifanaye and shit. Like you get like the power of C++ without the bullshit and with more guardrails without compromising like simplicity and ability to express yourself the way you want. It's like very, very nice that way. So like it seems nice. Like I don't really feel like I'm learning anything new writing it. When I wrote Rust, it felt like it like changed the way I thought about code. Where like this I don't feel like is doing that at all, but it does feel nice. I would reach for this in like cases where I would use C++. I don't know. Okay. So, we've successfully decoded after swapping these like tree for array structure. So what I want to do now is I want to see like how much fucking faster is that, right? Because my gut says that reading 7 bits from a time and indexing into this array is going to be way fucking faster. But it would be nice to prove that in some way. So let's see if we can do a test of some form. Let's do git status, git add-u, git commit-m, and we'll call this, maybe we'll take a new branch, and we'll say, oops, whip already exists, so I think that's nothing valuable, so we can just update refs, heads, whip, head, git checkout whip, git commit-m, and we'll say work in progress, array decoding of Huffman. And now we write a like little test in main. Let's delete this codebook shit. This like codebook printing. We don't need this anymore. But we do want something that is like, we're gonna write something with our codebook. So we can say like, well, we already have a way to, no, yeah, it's fine. We'll say, let me think. Let's make a Huffman writer with this codebook. And let's just like write in something that's like quite large. So we'll say var buff is equal stud array list of u8s. We're going to write in like a really long string. Can I do something like hello world and then like do this 100 times? Is this how Zig works? And then we can try to decode it with a Huffman reader. And how does this fucking thing work again? I need it. Okay, yeah, like this. Okay. So this says buff here. And here, I think we can use, we need to say var data is going to be this hello world shit. And then the output length is going to be data.len, or data.len. And can we like maybe stud debug print our decoded thing, just to see if we are decoding correctly, like I think we should be. Zig build run. Okay, not working. Because this has to be init with an allocator. Invalid type given to fixed buffer stream. Fuck yourself. This is buff items. Expected a const huffman table, but got non-pointer type. Dude, I implemented this the other day, and man, there's something about like the ability. This is so sick. I learned this is a new pattern unlocked for me, where like I'm generating some type based off of some inputs, and you can do all this like kind of slick little type checking, right? So I can say like I took in some any type, this like duck typed table, and then I can like check. It's like, well, I expected this thing to be a pointer. And I expected this pointer to have a child that matches a Huffman table. It's supposed to be a Huffman table. So I could build a new Huffman table based off the data type that I see inside it and check that it's the same. If it's not, then I get a nice little error. That's so slick. So slick. And now I have this like nice little Huffman reader requires a const Huffman table. Got non-pointer type. Look at that. Look at that sick error message. That's so slick. Oh, baby. Okay, so here I'm supposed to put like ampersand here. And then ret append val. We'll just put int cast here. Thanks for throwing answer. Like I said, I felt my question was really full phrase, meaning my question was mostly, are people going to adopt it? Blah, 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 blah. Felt like you especially answered, but I would recommend it. That applies a little bit of adoption. I think you said you would recommend a work setting. Yeah, I mean, it like depends on, like there's a lot of risk there, right? Like if you were to, like, I'll just say it has potential. Let's leave it at that. Okay, so he doesn't like format string s for this thing because I have to write items. Look at the little slices inside, not the outer structure. And it does look like we have generated a string, hello world, prints it 100 times. He decodes it. Everyone's happy. And I just have to say, please fucking don't leak my memory. We're missing another one at who am I not dealing here? Probably this guy. There we go. Okay. So let's kind of like just crank this guy up. It's like, I don't know, like 8,000 of them. Is that gonna like Stack Overflow? No, this stuff should end up not in the stack, right? I would expect that if I write this, hello world times 8,000 should end up just kind of hard-coded in the elf. But I could also see a world where the hello world gets hard-coded in the elf and the times 8,000 like copies that thing 8,000 times onto the stack. So I have to be a little careful about this. I don't actually know what this does. So maybe what we can do is we can build this thing. And we can just do a little bit of strings on the output. And grep for hello. And the fact that we see this giant chunk of hello worlds in the binary implies that it did that at compile time for us, which is great. That's what we want. Which means that I don't have to worry about like Stack Overflowing when I run this guy. Zig build run. Okay, so great. And now maybe we could do something like benchmark this whole section. So is there like a timing mechanism in the Zig standard library? Or at the very least a way for me to get like the monotonic clock? Should be. Monotonic. Yeah, okay. So there's at least stood OS, stood time instant. Great. Stood time timer. Perfect. A monotonic high performance timer. Timer start is used to initialize the timer. Gives the caller an opportunity to check for existence of a supported clock. That's so sick. Once a supported clock is discovered, it assumes that it'll be available for the duration of timer's use. Sure. Makes sense. So, okay. Stood time timer. And this is a struct, so do I have to initialize this guy? He initialized the timer by querying for a supported clock. Okay, so I just say timer start returns a timer. Ah, okay, sure. So I can just say var timer is equal to this thing, and then at the end of all of this, we can just say timer. I guess let's get our return kind of guy initialized before we start timing. Let's reserve. let's kind of init with a capacity of the expected output length to avoid realix while we're reading. So buff, this is data len, I guess, is the expected capacity. Let's ignore like construction of this guy. It's really here. This is where I want to log. And so at the end of this, I want to say stood debug print. Maybe we say var end is equal to timer. What does this guy give me? He gives me a lap reads the timer value since the start. Okay, yeah. So var time elapsed is going to be timer read, and then we just print this value. Took this much time, and what's the unit here? Reads in nanoseconds. So here we want to do like, what is it, int to float, or is it float from int? I guess we'll find out. Divided by 10, divided by 1,000, so that's no, that's micro milliseconds. Yeah. Maybe we want to do milliseconds. Milliseconds seems fine. Yeah. There's a ns per millisecond. Oh, nice. Yeah. Stood time divided by stood time ns per milliseconds, and this is going to be a constant, which I don't know if I have to float cast. Int to float doesn't exist, so float from int is probably it. And this guy needs to be like as f64 or something. Okay, and then init with capacity doesn't exist. I could have sworn I've seen this. Array list, init. Oh, it's just init capacity, not init with capacity. Of course. No method dinit on this thing because I have to try because I'm allocating memory now. And no function read in timer because I have to check if there's a supported clock, so I have to type try to propagate the errors. And let's not print out this bullshit at the end. And 1 millisecond is, oh, god damn it. I need to fucking, how do you do this again? You say like number, and I want like, do I just type D maybe? I can't remember. I'm gonna have to check. Okay, 10 milliseconds. So let's get a little longer. Let's do like 32,000 of these. We just want to get into like a range of something that's like sane. Maybe like that, like we'll see. I want to see something that's like significant time. So maybe we'll do like 100,000. Okay, 127 milliseconds. That's great. And then we also have to run in release mode. So there's probably some sort of like de optimize equal to release fast. I think probably makes sense there. What's happening? Okay, there we go. So that takes significantly faster, like an order of magnitude faster, which is pretty crazy. Let's new line here. And then let's just kind of slap on another 0. What? This is crazy. So whatever it's doing in this optimization paths is taking a fucking long time. And then you know what would also be kind of fun? Is if we GDB zig out this guy. And I don't know if we lose debug symbols here. Looks like no. And it would be kind of fun to look at, like, what the fuck does this guy do? Oopsies. I think I broke at the wrong line. I want to break probably at 214. Main zig 214 run. Okay. So can we disassemble? And I don't know if I'm going to see anything that like makes any fucking sense to me. But it would be cool if we could. Yeah, I don't know what I fucking thought was gonna happen here. This is a lot of stuff, and I don't understand it at all. Okay, well, it was. I was kind of hoping that we would see something interesting. But like, yeah, it's not clear at all. Okay, anyways, let's see. Zig build run. So this took 88 milliseconds. And can we compare that to the old way? So can we maybe... Oh, GPA is super slow. Good to know. That's interesting. I wonder... I think that our timer should not end up allocating anything. Reader next. So our Huffman reader, when we call next on him, there is no allocating in here, I don't think. Unless like the file reader is doing some allocations under the hood. I guess probably we should also check if we should do buffered IO if we're not. But we I guess if everything else stays the same, maybe it's fine. Let's go see if we see like a significant difference. That's fine. Okay, so Zig build run. Get fixed Huffman table is not marked pub because I reverted. Right, get fixed. Get fixed. Okay. So we were looking at, what was it, 88 milliseconds or something? 205 milliseconds. 206. So we're significantly getting like 205 here. And if we go back, git commit -m back out. Here, with the array version, we're getting... That would be weird because no hidden memory allocation. Oh yeah, that's right. I never pass an allocator into the file streams, so I can expect that they don't. Okay, so not really as much of a speed up as I was really imagining. That's like maybe like just over a 2x speed up, right? We go from 200 to 88 or 89. I would be curious though. I wonder how much faster it is in debug mode. Because I would have just assumed that reading bit by bit, and walking a tree would just be so much fucking slower. That would have been my assumption. So in debug, we're at 1252 on the new one. And let's see where the old one. Yeah, that's again like about 2x. But I guess you could also, we would have to, what we should probably do is record performance with perf and see how much of that time is actually being spent in the decoding. Because it could be that we're like spending a lot of time somewhere else now, and that's like completely dominating the performance. So maybe if we go here and we Zig build with optimize release fast, blah, blah, blah. And can we perf record -d call graph equals dwarf zig out blah blah blah, and I need to download perf, so nix shell linux kernel, I think it's linux packages latest dot perf, because I don't remember which of these guys I'm on, so I think this will just tell me to use whichever one is available. And if I perf record perf script and then output to test perf, and then I open Firefox and I go Firefox perf. I can't remember what it's called, but Mozilla has a profiler website, and I can say load profile from file, and we can look at our this guy, and we can see where the fuck all the time's going. Yeah, so that's interesting. So self 39 in Huffman Reader. Yeah, interesting. So we're seeing most of the time it looks like. So we're seeing about 25% of the time in the Huffman reader and around 25% of the time in like bit reader. Okay. And on the old version, so let's maybe copy this. Or I guess we can just open it in a new tab when we do this again. Perf record. Perf script. And then we just go back to profiler.firefox.com again. And here it's a lot more in the Huffman reader. So we're still at around 25% of total time in the bit reader. But keep in mind that 25% of time is more. And then 75%. So it looks like we kind of like halved the amount of time we're spending in file IO. And then this guy went from 75% down to 25%, but that 25% is half as much. So we like quadrupled-ish performance of like the actual array lookup, I think, if I did the math in my head right, which I probably didn't. But okay, so that's not bad. I was expecting more, to be honest. I was expecting that reading bit by bit and walking that tree would be slow as fuck. Not like not like double speed or double time of array lookup. So that's interesting. Pretty cool. Fun stuff. I think I've accomplished what I wanted to accomplish. There's like some cleanup to be done here for sure, right? Like we didn't really handle some of the other initialization cases. This like codebook generation with the new way is going to be much easier. So so first of all, initializing this guy from the bit lengths now, that's going to be much easier. Can you see how many cycles it takes? This is 820 or 552 cycles here versus 119. So yeah, about 4x. Wait, hold on. Sorry. 93 versus 552. So 5x. Not bad at all. I guess cycles is the wrong word here. This is probably samples. So assuming that we're sampling at a fixed rate, then we can expect a similar amount of time. But I don't know if I see number of cycles in here. So this init for bit lengths function, what we were doing before was we were constructing a codebook, then iterating our codebook bit by bit and constructing the tree based off that. This should get like way simpler now with like the array format. Instead of having to build a tree, we just kind of say for each code at this bit length, just copy paste it into the array. So that should make that super easy. Codebook generation, we had to like walk the tree, do like a DFS, and then for each leaf node, like keep track of the path and then like convert that path into a code. This should also be way easier now. All we have to do is iterate the arrays and just like sequentially jump out numbers. So pretty super cool there. And then reading is simpler. The only thing that we like still need this tree logic for is the nodes, the actual generation of the tree initially to figure out how many bits each character should take. So I think this is going to result in 2x speed up, much simpler code, overall better understanding of the algorithm, right? Like the idea that like packing this stuff into arrays just makes way more sense than walking the tree, like to me mentally. So it means that I get it better. So even though it was only a 2x speed up, I think I am happy with the change, and I'll probably like off stream just go through and do all the rest of the cleanup that's necessary. So thanks for watching, guys. If you liked what you saw, we stream most days at around 2 o'clock Pacific time. So it's 4 o'clock now Pacific time. So anywhere between 2 hours ago and now, we usually stream for around 2 hours. That's kind of like a good balance of YouTube VOD that was like actually watchable and Twitch stream. Arguably, those two things should be segmented, but for the time being, since we're doing this for fun, we want to keep them around the same. So that's there. YouTube VODs are in the Twitch description. There's a YouTube channel link there. So we've covered like some other stuff. We've done a lot of like Rust, low level trending. So we did like a Rust operating system. We did some like neural network stuff in Python. We did some like we've done like a little bit of web dev, not a lot. Like virtual file system, some like 3D geometry stuff. So there's like some stuff in there if you want to go look. There's a GitHub link in the Twitch description as well with code for everything ends up eventually. If you don't see the links, same username on everything. And if you are on YouTube and you made it this far into the VOD, there's a good chance that you might want to swing by and say hi if you happen to be around when we're live. So check out the Twitch link in the YouTube description. I think that is it. Thanks for watching, guys, and I'll catch you on the next one. Bye!